Welcome to phase 4 of our series Advanced Architectures and Innovations. Today we're exploring Mixture of Experts or MoE.
MoE is one of the most exciting architectural innovations for scaling LLMs efficiently. Let's start with the core concept. What is a mixture of experts model? An MoE model contains multiple expert networks, separate submodels that specialize in different aspects of the input.
Instead of processing every input through all parameters, a routing mechanism selects which expert should handle each input. This makes the model sparse. Only a subset of parameters are active for any given input. The key advantage is that you can have a model with billions or trillions of parameters total, but only activate a fraction for each input.
This means you get the capacity of a large model with the computational cost of a smaller one.
Let's talk about the architecture. How does routing work?
There's a gating network or router that looks at the input and decides which experts to activate.
For each token, the router computes scores for all experts, typically using a softmax over learned parameters. Then you select the top k experts, commonly k equals 2, meaning each token is processed by 2 experts. The experts process the token in parallel, and their outputs are combined using the router scores as weights.
So if expert A has a score of zero point 0.7 and expert B has zero point 0.3, the final output is zero point 0.7 times expert A's output plus zero point 0.3 times expert B's output.
The experts themselves are typically feed-forward networks, replacing the standard FFN layers in transformers.
So a transformer with MoE has normal attention layers, but the feed-forward layers are replaced with MoE layers.
Each expert is a FFN with the same architecture but different learned parameters.
Let's discuss training challenges with MoE.
One major challenge is load balancing. You don't want all inputs routed to the same few experts.
If that happens, some experts get overtrained while others are underutilized, wasting capacity.
To prevent this, you add an auxiliary load balancing loss that encourages even distribution of inputs across experts.
This loss penalizes the model when routing is too imbalanced.
Another training challenge is stability. MoE models can be harder to train than dense models.
The routing decisions create discrete choices, which can be unstable during training.
Techniques like adding noise to router scores or using softer routing help stabilize training.
There's also the challenge of communication overhead in distributed training.
Experts are typically distributed across different GPUs or machines.
When a token needs to be processed by an expert on a different device, you need to communicate.
This all to all communication can become a bottleneck, especially with many experts.
Researchers use various optimizations like expert parallelism strategies to minimize communication.
Let's talk about the benefits of MoE beyond parameter efficiency.
MoE allows specialization. Different experts can learn to handle different types of inputs or languages.
For example, in a multilingual model, different experts might specialize in different languages.
Or in a general model, some experts might handle code, others factual questions, others creative writing.
This specialization can improve performance compared to a dense model of the same size.
MoE also enables scaling to much larger total parameter counts than would be practical with dense models.
GPT-4 is rumored to use MoE, though the details aren't public. Mixtral from Mistral AI is an open MoE model.
Mixture 8x7b has 8 experts, each 7 billion parameters, but only activates 2 experts per token.
So it has 47 billion total parameters, but the compute per token is similar to a 14 billion parameter dense model.
This gives it performance competitive with much larger dense models at lower inference cost.
Let's discuss variants of MoE architectures.
Top K routing is the standard. Activate the K experts with highest scores.
But there's also top 1 routing, where each token goes to a single expert.
This is more efficient but might reduce quality.
Soft MoE uses soft mixing, where all experts contribute, weighted by router scores rather than hard top K selection.
This is differentiable and can be easier to train but less sparse.
Expert choice routing flips the paradigm. Experts choose which tokens to process rather than tokens choosing experts.
This can improve load balancing and efficiency.
Another variant is hierarchical MoE, where you have multiple levels of routing.
First, route to a group of experts, then within that group to a specific expert.
This can scale to very large numbers of experts more efficiently.
Let's talk about MoE for different modalities.
MoE isn't limited to language, it's been applied to vision models and multimodal models.
In vision transformers with MoE, different experts might specialize in different types of visual patterns.
For multimodal models, experts might specialize in different modalities or cross modal interactions.
MoE has also been used in diffusion models for image generation.
Now, what about inference with MoE models?
Inference is more complex than dense models because you need to route each token and activate the right experts. If experts are on different devices, you need to handle the communication. But the active parameter count is much smaller than total parameters, making inference faster than a dense model of equivalent total size.
You do need to load all expert parameters into memory across your devices, so memory footprint is based on total parameters.
But computation is based on active parameters, giving you speed advantages.
Let's discuss how MoE relates to model capacity.
Capacity refers to the model's ability to learn and represent complex functions.
MoE increases capacity by adding more parameters without proportionally increasing computation.
This lets you build models with greater representational power for the same training and inference budget.
But there are diminishing returns. Simply adding more experts doesn't always improve performance.
You need sufficient task diversity for the experts to specialize meaningfully.
And there's overhead from routing and load balancing that limits the efficiency gains.
Research suggests that somewhere between 8 and 64 experts is a sweet spot for many applications, though this varies.
What about fine tuning MoE models?
You can fine tune the entire model, including all experts and the router.
Or you can use parameter efficient methods, training adapters within each expert.
Another approach is to freeze most experts and only fine tune a subset, or add new task specific experts.
The modular nature of MoE lends itself well to compositional fine tuning strategies.
Let's talk about the future of MoE.
There's ongoing research into better routing algorithms that are more stable and efficient.
Work on dynamic expert allocation, changing the number of active experts based on input difficulty.
Exploration of MoE combined with other efficiency techniques like quantization or pruning.
An interest in MoE for personalization, different experts for different users or contexts.
There's also research into learned sparsity more generally, where MoE is one example.
The idea is to activate different parts of the model for different inputs, making models adaptive and efficient.
MoE represents a shift from homogeneous dense models to heterogeneous sparse models.
This aligns more with biological neural networks, which are also sparse and specialized.
So, to recap, Mixture of Experts uses sparse routing to activate different expert subnetworks for different inputs. This enables larger total capacity with lower per input computation. Routing and load balancing are key challenges. MoE allows specialization and efficient scaling, and it's being adopted in frontier models for better performance efficiency trade offs.
Next episode, we're exploring test time scaling techniques to improve model performance during inference.
Thanks for listening.
Until next time, keep learning and stay curious about AI.